What to do, squad? Thank you for tuning in today. I'm gonna get right to the point. We solving a problem today. This is the problem I've picked out from the relativity chapter, chapter 39. I got a black background here today because it hurts the eyes, but I'm gonna scroll back to the book real quick just to show y'all where this problem is coming from. We got over here, chapter 39, relativity. Under this section here, problems related to these three concepts. I picked the first problem, problem number 5. Let's read it together. A star, actually, I'm going to outline some important stuff too. A star is 5 Ly from the Earth. Sentence 1. I'm going to just circle this. This is a number, pretty important. At what speed must a spacecraft travel? Okay, so it's asking us the speed on its journey to the star such that the Earth-star distance measured in the frame of the spacecraft is 2 Ly. Okay, so we got 2 Ly, 5 Ly. These are the only two numbers in the word problem, so more likely than not, we're going to be using these bad boys. Here is the question: at what speed? Actually, I'm going to put this in red over here because this is what we need to answer. At what speed must a spacecraft travel on its journey to the star? So they talk about the star here and they talk about the star here. Maybe I should put these in yellow. Star, star. I'll also put a little box around Earth, also important. At what speed must a spacecraft travel on its journey to the star such that the Earth-star distance, this is an interesting little thing here. What does the Earth-star distance mean? We already outlined star and Earth, and we see those bad boys right here. The Earth-star distance measured in the frame of the spacecraft. This is also kind of an interesting little part of the sentence here. And we got the number over here. So just outlining some words. Let me erase this right here and draw like a nice looking picture. So what we got is the star, right? And we got Earth right here somewhere. Earth star distance, I would assume, just means this. Distance, the distance from the Earth to the star. A star is 5 light years from the Earth. Okay, so this equals 5.00 light years. And light years is something that you may have not seen before. I'm just telling you, this means light years. What does it mean? Distance. Light travels in 1 year. So remember, velocity is equal to meters per second, which is distance over time, right? We know the speed of light is 3 times 10 to the 8 meters per second. And 1 year is equal to, oh man, how many seconds? So we got 60 seconds per 1 minute. We got 60 minutes per 1 hour. I'm doing this because minutes here cancels with minutes here. 60 seconds per hour. Hours. I'm trying to cancel hours here with days. So we have 24 hours in a day. I'm going to just move this over here. Maybe this is not too important. I'm kind of just thinking out loud here. You might solve this problem differently. So 60 seconds per minute, 60 minutes per hour, 24 hours in a day, and 365 days per year. Okay, so basically what I'm trying to do here is calculate how many seconds are in a year. So we have seconds here which are left. Minutes cancels with minutes, hours cancels with hours, days with days, and we have year over here. So at this final equality, the units are seconds per year. And since we have nothing in the denominator, we can assume this is 1. So what do we have here? I have 60 times 60 times 24 times 365. Damn, that's a big number. I'm going to need to pull out my calculator. I do not want to waste your time doing some goofy mental math. 60 times 60 times 24, 86,400 times 365. Holy shit. This is a big number. 31,536,000. That's how many seconds are in 1 year. Okay, why am I doing this? Because if we take this equation over here and we plug in this amount of seconds over here, we can calculate the distance that light travels in 1 year, which is 1 light year. Honestly, it's not too important. You're really not going to use this to solve this problem. I'm just showing you, like, if you know what light year means, this definition, you can kind of pull out a bunch of math out of your ass just by thinking about it like normally, logically, right? And this is not important for the problem. I'm showing you just a little side segue. Maybe there's a waste of time here, but let me take a sip of tea. I was actually planning on solving this problem pretty quickly and just spitting out a quick video, but now that I'm talking about fucking light years in terms of meters per second. Anyway, at the end of this calculation, we're going to get light year in meters. So how do we get that? I'm going to pull this equation down here. What do we have here? We have distance equals velocity times time, right? So this equals 3 times 10 to the 8 meters per second. That is the velocity of light. We multiply this by 31,536,000. This is seconds per 1 year. All right. We can see that if we multiply these two, seconds cancels with seconds. And we get at the end, right? At the end, we're trying to find this distance. This distance is equivalent to 1 light year. So 3 times 10 to the 8 is a huge number. I need to use some exponential notation here. 3 times 10 to the power of 8. 300 million. Multiply that by 31,536,000. Damn. Okay. Whoops. Pull this shit out of the way. Grab this. Slide it over so it looks clean. What is this number? 9.4608 times 10 to the 15. What are the units left? We have meters per year. So what is 1 light year? It is a distance. Literally as simple as that. 1 light year is just a distance. It's like converting from this to kilometers, to meters, to miles, to nanometers, whatever distance and unit you want to use. Light years is just a distance. What is that distance? It's the distance light, which is this letter right here, light, takes to travel in 1 year. And that is this whole calculation I showed you here. I kind of just pulled it out of my ass just by the definition of light years, this velocity equation, the speed of light, and like this little calculation of how many seconds are in a year. And we find out that 1 light year is equivalent to 9 times 10 to the 15 meters per year, right? The unit there is per year because we're talking about light years. You can talk about light seconds, light minute, light hour, whatever. It's the same kind of thing. How much time does it take? How much distance does light cover after this amount of time? In this case, it's year. So this is a huge number. This is 94608. Actually, wait, that's kind of stupid. It's like 9 with 15 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Boom. I don't know what number this is. This is 1,000 million, billion. Is that true? Billion, trillion, quadrillion? Is this quintillion? I have no idea, guys. This is a lot of meters. So long, long, long distance, uh, astronomical distances. Anywho, we're going to go back to the problem. What the hell are we talking about here? A star is 5 light years away from Earth, long distance. At what speed must a spacecraft travel on its journey to the star such that the Earth-star distance measured in the frame of the spacecraft is 2 light years? So let's outline the important problems. We have 5 light years here, and we have a spacecraft on its journey to the star. So we have a spacecraft right here, right? Little spacecraft going this direction. At what speed must the spacecraft travel on its journey to the star such that the Earth-star distance measured in the frame of the spacecraft? Okay, so we have frame of spacecraft. Frame of spacecraft, 2 years. 2.00 light years? Question mark, question mark. I'm not too sure what to do with this number, but it's important, and it is connected to the frame of spacecraft. The frame of the spacecraft. Maybe I should outline this frame here in yellow. I don't know, I'm putting a frame because I'm thinking of like a picture frame, right? We got shit right here. Let's see where they use the frame, if they use the frame anywhere else. A star is 5 light years from the Earth. At what speed must the spacecraft travel on its journey to the star such that the Earth-star distance measured in the frame of the spacecraft is 2 light years? Okay, so we have 5 light years here, 2 light years here. Interesting. So this distance here, 5 light years, is bigger than this distance, right? It's like a bit more than 2 times bigger. So the spacecraft here is traveling this distance of 5 light years. It starts at Earth, it starts going over here to the star, and this distance it's trying to cover is 5 light years. But we are told the spacecraft sees it as if it's 2 light years. So this is why this problem is in the relativity section. Relativity, because a consequence of traveling really fast, and we're going to see how fast exactly because we are going to calculate the speed of the spacecraft to solve the problem. A consequence of traveling really fast, as per Einstein's theory of relativity, states that length contracts. So, consequence of moving fast. We got one of them, length contracts. We got another one, which is time dilates, but I have not done a time dilation problem. This one is important. We're going to check it in a future video. We got some other consequences here, 3, 4, 5, whatever onwards, but length contraction and time dilation are one of the main ones. And what I'm sharing with you guys here today, this is why you start reading the theory about the books first to see kind of how you can solve this problem, because reading this problem just as a sentence, it's 2 sentences, and it's fucking crazy. Like, what are we supposed to pull out of this problem? I circled every important word, I drew everything, I talked about light year for a fucking 2 minutes, or even longer, I don't know, bro. But you need to read the theory because then things are going to jump out at you super quick. So since I know it's in chapter relativity, but I'm not too sure from where, I'm going to pull out the book. Sorry if it is too bright. And I'm going to outline the problem here and just scroll up in the book to see what's happening. Normally problems are at the end of the chapter. Or here you see if you scroll up, you got some other problems. And here is the summary. Check the video where I go over all of this. But right now, since I'm solving a problem and I can't remember anything about what I read, I'm just going to quickly look at the summary over here because I think it'll be helpful. Let's take a look at things that include distances like light years. So this first box, we have the relativistic expression for linear momentum of a moving particle is this. Momentum might be a bit helpful. They are asking about speed, and speed is related to momentum, but I don't think this is important here. I'm just going with my gut. relativistic force acting on a particle. We don't have any forces in this problem. Again, momentum is like slightly related, but we don't have any information. All we have is light years, distances from Earth, shit like that. We're looking for a speed as well. Two basic postulates of special relativity. Maybe this is important. Laws of physics must be the same in all inertial reference frames. Okay, we did talk about frames of reference. Inertial reference frame, though, I'm not sure if it's too helpful here. Speed of light in a vacuum has the same value, 3 times 10 to the 8 meters per second in all inertial frames, regardless of the velocity of the observer, of the velocity of the source emitting the. Okay, it seems kind of roughly helpful. I mean, I did remember this fact. Light speed is this distance, but still, I'm not too sure how to use this to solve my problem. Let's take a look at this. 3 consequences of the special theory of relativity. Okay, I shared with you guys the consequences of moving fast. This, I think, was a little segue. This, I think, will be important. Events that are measured to be simultaneous for one observer are not necessarily measured to be simultaneous for another observer who is in motion relative to the first. That is crazy, and I don't know if it's too helpful. I mean, we're going to keep reading. Clocks in motion relative to an observer are measured to run slower by a factor of Greek letter gamma equals 1 minus v squared minus c squared. Okay, we have v, which is a velocity. That is interesting. This phenomena is known as time dilation in bold, and I told you guys this is one of the consequences. I was kind of leading up to this. Let's read the last one. The lengths of objects in motion are measured to be shorter in the direction of motion by a factor of 1 over gamma equals 1 minus all this bullshit here. This phenomenon is known as length contraction. This is exactly what I was trying to kind of lead you guys into. And if you read a bit of the theory, this should jump out at you when you see problems that include changing length, asking you for speed, shit like this. So take a look at this. Boom. This singular sentence, if you kind of just study it a bit, ponder it, you will see how it helps you solve the problem. You need to think about this. Otherwise, if you have never heard of this, it's going to be crazy solving the problem. You literally got to think of this from the freaking boot like Einstein did. So it's very tough. Now, we know that we are talking about length contraction, and I want to use an equation. Like, I know this here is an equation, but like gamma, I've never seen gamma before use an equation. I have V, I have C here, but I need something that relates length. Remember, because in the problem, I have 2 lengths. I have length 5 light years over here and length 2 light years over here. And what I'm actually looking for is a speed. So I want to find an equation that relates all these 3 here, knowns and unknowns. If I can find an equation like that and it is related to length contraction, I know I'm on the right path. So I'm going to just scroll up in this chapter, kind of like keep my eye on like problems and just remember the 5-7 minute summaries or things like this that I do, and try to find an equation that could help me. I'm also just looking for the section, like here, relativistic linear momentum. This I know is not useful to me. And I've just taken a big gander of the chapter, so I kind of have an idea of where this is supposed to be and what I'm looking for. I'm basically looking for the word length contraction, or these Lorentz things are kind of close to what I'm looking for. Doppler effect, no. The Pullman-Barn paradox, what is that? Voyage to Sirius. An astronaut takes a trip to Sirius, which is located at a distance 8 light years from Earth. Okay, crazy. An astronaut measures the time of one-way journey to be 6 years. This is looking familiar. If the spaceship moves at a constant speed of this, how can the 8 light year distance be equaled with the 6? Okay, this problem looks extremely familiar. Space-time graphs. Let me peep. Here it is. Okay, this is exactly what I'm looking for. Length contraction, boom. This is under the section length contraction. Okay, solid. And the twin paradox. What section is this? Let me just peep the section really quick. Damn, this is a long section. Time delay. Okay, this is the big section. Consequences of special theory of relativity. I have not read this in the YouTube channel yet. I think I stopped before this, but there's a lot of interesting stuff. This section, crazy. This section, absolutely crazy. And I think time dilation caps it off. Or sorry, my bad. Length contraction. How long was your trip? This also looks like an interesting example. And they solve it here for you, and they use some kind of gamma related thing. The twin paradox, okay. Basically, this length contraction, I'm telling you guys, has the answer to this question. And it is for sure this equation. Save that photo. And if you are interested in solving a problem on example first, take a look at this one, take a look at some of the other examples. If you really have no idea on how to solve something like this without looking online, trying to find a solution online, and you want to solve it like organically on your own, just sitting with a piece of paper, take a look at some of the examples done in the book, like this voyage. This should help you quite a lot. It'll give you ideas of where to start. Okay, so what I have been arguing here is that this equation here is important. So let's take a look at this. We got L, we got LP, we got gamma, and another way of writing this is LP over here. Maybe I should be using red. LP right here, we got L, we got gamma, and we have another way of writing it, LP. LP is being multiplied by this huge thing here. Inside it has c squared, which is the speed of light squared, which we know, 1 we know, and v is a velocity. So just like how I told you guys before, we need to relate the velocity and the two lengths here. We have one length over here, one length over here, and a velocity over here. So the singular equation includes everything that our problem is talking about. This is why it's important drawing a picture, taking a look at the problem, thinking about the theory a bit. But since I don't really know what this length, all this stuff means, I'm gonna just go back to the chapter really quickly and peep the equation. So let's take a look at this. Because the proper length is LPV delta T, we see that, and then they include this equation here. Let's read underneath here, where this factor is less than unity. Unity over here normally means 1. So this entire bracket here is less than 1. Also remember, one of the postulates of special theory of relativity is nothing can go faster than the speed of light. This v normally is equal to c or less than c. It cannot be bigger than c. So because of that, that's normally why this thing is less than 1. You can do some math there to check. You can also check the graph of gamma, which I don't think I've talked about yet. I don't know. If an object has proper length, LP, when it is measured by an observer at rest with respect to the object, its length L, when it moves with the speed v in a direction parallel to its length, is measured to be shorter according to equation 39.9. Okay, so proper length LP is the length when the thing is measured by an observer at rest with respect to the object. That might sound a bit confusing. This is why this chapter is pretty confusing. You got to talk about reference frames, different objects. But remember that we did actually talk about this when we were reading the problem. We saw the word frame of blank. For an example, a meter stick moves past a stationary Earth-based observer with speed v, as in figure blank. The length of the meter stick as measured by an observer in a frame attached to the stick is the proper length LP shown in figure blank. The length of the stick L measured by the Earth observer is shorter than LP by a factor blank. So we know that we are told that in this meter stick example, L is shorter than LP. Okay, let's take a look at this. Okay, this picture is getting a little crowded, so I'm gonna just redraw it here. Let's peep this. We got here sun, we got here Earth, we got this distance here between them, which is 5 light years, and we got a spacecraft here traveling like this, and in its reference frame, it sees 2 light years. Okay, so we just saw that the proper length has to be longer than this length here without the little p on it. And we also saw that this factor, actually I'm going to draw this here in green. So square root 1 minus v squared over c squared has to be less than 1, less than unity. So it can be like 0.1, 0.5, 0.9, anything. It can't be 0 though, because here you have 1 minus something that is non-negative. It's a square root, whatever. You could just have positive numbers between 0 and 1. So your number is somewhere in here. If you multiply LP by something between 0 and 1, the thing it spits out must be less than LP. So L must be less than LP. That's why they call this length contraction. When you talk about contraction, it normally means getting smaller. Like a turtle contracts its neck, an excavator contracts its claw. I don't know what I'm saying here, but your muscle contracts. I don't know. Anywho, I'm kind of just using a bit of the information they give me in the section of the book to make sense of this problem. Try not to Google search anything. Try to just explain shit to myself and see if I can piece the problem together. This is a little section that I had before. Insert space, move this down real quick. Okay, so let's see. So from this argument, we are saying that L must be less than LP. So from this analogy, I think LP is this 5 years and L is this 2 years, right? Because L is the contracted length because the observer is moving really fast with a velocity v. Okay, interesting. So now that we have this equation, let's actually piece the equation together. So we have L equals LP over gamma, which I guess we could say is 2Ly equals 5Ly over gamma. And you see how the light years are not important. Here we have light years, here we have light years, they cancel. We didn't need to go through this entire explanation here to convert light year into meters. I was just talking about that because I found it kind of interesting. I hope you found it interesting too. But we have another equality here. We have LP over gamma, and we have L, whoops, let's use white over here. L equals LP times the square root 1 minus V squared over C squared. Is that true? That looks true to me. We're going to add this here. Let me add a little space here. Actually, let me move this down here. So I said L is 2 light years. This equals LP is 5 light years. Square root 1 minus V squared over C squared. Cool. So if we divide both sides by 5, let's just work with this equation here because I want to isolate for V. If we take this equation, let's go here, and we have 2 light years over 5 light years. On the other side, we have square root 1 minus V squared over C squared. Light years here cancels with light years. 2 divided by 5 is it 0.2? Let me actually check this. 2 divided by 5. 0.4. I'm a geek. Wait a second. Am I doing this right? 2 divided by 5. I guess that makes sense because you multiply both by 2. You get 4 over 10. So I was mistaken here. But take a look at this. This actually fits with our theory because we did say that the number here, gamma, this thing right here, has to be less than 1. Has to be somewhere between 0 and 1. And what we got here is this thing is equal to 0.4, which checks with our theory. You always want to make sure what you're doing in your math makes sense like this. No need to remember it, but it's kind of useful. Sometimes you might check, like spot some errors beforehand if you follow that rule. Okay, let's peep what we can do here. So let me just rewrite the equation. 0.4 equals square root 1 minus V squared C squared. Interesting. I guess what we can do is square both sides. 0.4 squared equals 1 minus V squared C squared. I guess we can add this to this side and subtract this from this side. So we have V squared C squared is equal to 1 minus 0.4 squared. 0.4 squared. Okay. So let's actually calculate that. 0.4, oops. 0.4 times 0.4. 0.161 minus 0.16, 0.84. U squared c squared, 0.84. Okay, at this stage, keep in mind what you want to find is v, because my whole argument here is that this v is equivalent to the speed of the spaceship, which is exactly what we're looking for, right? Do I have a laser pointer here? I don't think I don't. But right here in green, it says what is the speed of the spacecraft. My whole argument by showing you this kind of analysis here is that this v, which came from the equation that included gamma over here, right? This is gamma, a different definition of gamma. We got v over here. My argument here is that this v is the exact v of the spaceship. If you want, what you could do now is plug in 3 times 10 to the 8 meters per second squared, solve for v, square root both sides, whatever. You have this little here thing to keep track of the algebra, and you can calculate the speed of the spaceship in meters per second. But what you could do at this stage actually is just take this c squared and multiply it on this side. What you will get is this. Okay, and you can square root both sides. On this side you get v. This square root cancels this here, so the square root just applies to the 84 or 0.84, and what we get is 0.9165. 15, yeah, whatever, c. Or we can round this down to 0.92c. Boom. Okay, this is a speed. It is in terms of c. It is 92% the speed of light. 0.92 times c is like saying 92% the speed of light. So one of the main postulates of special relativity is not broken. The velocity of this spacecraft is less than the speed of light. If it was more than the speed of light, like 3c, 4c, 15c, you're fucked. If it is anything close to the speed of light, like 90% the speed of light, 80, even 70, sometimes even 60, then you know that relativistic effects apply. But if it is something really small, like 0.0001c, relativistic effects don't apply too much. The gamma is really close to 1, this gamma here. So if this is really close to 1, you don't get length contraction, you don't get time dilation, you don't get any of the relativistic effects. So a couple of things that I'm keeping in mind. This is the answer that I got. I don't want to make this video too long. I'm going to check the back of the book. This is the answer, 0.917. 0.917. Okay, we did get the exact same number, but I think the book made a mistake here. It's supposed to be 0.917% the speed of light. Okay, like they don't put the c there. I don't know if that's anything kind of weird about it, but anywho, thank you guys for watching this video. I hope this was fucking helpful, man. I don't know, I know I kind of rambled quite a lot. I'm just showing you that like solving these problems on your own is very important. This is kind of me just spewing out my information. Like I just picked the first problem I saw in the book. I kind of thought about it a little bit. How am I going to do this video? What am I going to do? What am I going to say to these guys? And I kind of just went on without doing the problem first. I was just thinking about random shit as I speak and solve the problem with you guys here today. I urge you guys to do the same thing. Don't just look at solutions. If you think of a way to solve a problem and it's the incorrect path, like for example, here today I just shared with you guys this equation here, the length contraction one. If you didn't know that was the way to go forward and you tried some other route, maybe you're like, oh, Lorentz transform or some other equation there that I looked at the beginning. You thought, hey, this could be used to solve the problem. Please proceed with that and try to solve it, bro. Even if you're just brute forcing something, you're like, this looks messy. I have no idea what I'm doing. I don't even know if this is right. This is still immensely valuable to do. You know why? Because it is kind of like shooting a basketball. You're never going to be able to get 3-pointers over and over and over unless you shoot basketballs and miss 1,000 times. If you go and shoot and miss 1,000 times, eventually you're going to get it in. But if you never shoot and you just look at people shooting, maybe you'll get good. Maybe you'll get one right here, get one right there. But if you try on your own, you're going to calibrate much better. Even if you do the problem incorrectly, like you airball, you are still benefiting because you're practicing. So practice this, try this problem on your own. I didn't say that in the beginning of the video, but you could take a look at the textbook, open up any textbook page on the relativity section, or this applies to any chapter at all. Take a look at the problems, start it, at least write the problem down. That's the first thing you gotta do, just write it down on a piece of paper, look at it for a couple minutes, and then do what I did here. Take a couple different pens, like different colors, kind of helps me. Draw different circles, triangles, whatever, around each important word. Numbers, try to draw a picture, please draw a picture. I don't care how goofy it is, guys, draw a picture. You get points on this in an exam. And try to explain the problem to yourself. Think about it for like 10 minutes, 20 minutes, 30 minutes. Spend an hour thinking about it. Do not look at a solution, just think about it. Maybe read some theory, maybe look at some examples in the book, but try to organically solve the problem on your own. Try not to go on a YouTube tutorial. This is a YouTube tutorial, so thank you guys for watching. Drop a like and subscribe. But anyway, I'm just urging you guys to try the problems on your own. Maybe I'm yapping too much. Thank you guys as always for watching. Let me know if you have some questions down below. I'm going to do some other problems here if it's helpful for you guys. Peace.